here. Yep, this is the one. Sorry, no. This is a okay. You mean I didn't put down? Okay, forget to put out 2233 lecture. Because I thought there's a break, okay, so I only pull it out after the break. Okay. Yeah, I have done this one. Okay, so after doing the tutorial, okay, you are going to find that, okay, some of this part here, I can actually just go through very fast, okay? So we continue, yeah, forget to record. The recording. Okay, for this VHDL here, you find that there are very strong types of coding. So all VHDL data object must have a type. Meaning that, okay, if you want to use any of this information here, you must be able to tell what type of signal or what type of variables that, not to say variable, information that they are supposed to receive, okay? So every port, input output ports, okay, are declared in the entity must contain a type. That means that the type of information that they are going to receive, including the wire, your variables, your constants also, you must declare their types, okay? In this part here, you declare in the architecture. Okay, so VHDL is a very strong types of coding. So your types here, okay, can be, okay, those are standard package, okay. So if you are using those standard package here, of course, you have to call out the IEEE standard logic 1164 package types, okay, if you are using standard package. Other than this, okay, you can generate your own types. We are going to see this, okay, user defined. You can generate your own type. This is what I coded, okay, last time, that traffic light. Traffic light is in terms of color, green color, orange, and your red, right? So you are going to declare your own types if you are something like writing a code for traffic light. Okay, so next we proceed. So you are going to find that, okay, in this standard package here, those are predefined VHDL data types here are always, okay, visible lah. Okay, you no need to declare, like I said that, oh, okay, standard logic, things like that. So understood that what is a standard logic. If I declare as bit, understood that what is a bits here. So you use the word, for example, okay, types, you use the word Boolean. Understood that, okay, Booleans cover true and false. Okay, true and false. So although you may say that, oh, okay, false is 0 lah, true is 1, but theoretically Boolean, okay, indicating is true and false rather than 0 or 1, means right or wrong. Okay, the right or wrong. If it's bit so it contains, okay, the label of very ideal 0, very ideal 1. And if you are dealing with bit, okay, those logical bit always, okay, you have this inverted comma, then the logical value inside it. Okay, so if we see this, it indicates it's a logic. If I see this one and this one, it could be it's a number, okay, or integer. Okay, so if you are using bit, okay, you put down the word here, bit, understood, because it's already predefined. Okay, so this bit contains logic 0 and logic 1. So if I want to have a series of bit combinations, So we go for array. Okay, so you can use bit vector. Bit vector means that, okay, it can be 0, 1. So this is a not AND gate, but it's a series of combination. Okay, so if you are using, okay, bit vector like in this form, remember this one? Just now I say inverted comma one time. So this one double. Okay, let's say, okay, 3 bit 0, 1, 0. You also use double. 4 bit. Okay, double. So this is the bit vector. So you must declare the length, say like 2 down to 0 or 1 down to 0. If it's 2 bit, this is 1 down to 0, 2 down to 0, 3 down to 0, which is 4 bit. Okay, so if you declare, okay, certain number as integer, their range will be of this form. It's a very big number. No need to remember. So it tells you that, okay, very big, okay, range of informations. Then you can have a character, natural, positive, string, real time, the real number. Okay, the time usually will be in terms of nanosecond or picoseconds, I think. So these are the more common one we normally use. Okay. So all these are already predefined in this standard package of IEEE. Okay, it's already predefined. Okay, next. So in this IEEE, okay, 1076 1987, you also have integer types whereby they allow, okay, mathematical integer. So if this is the case here, okay, it's 32-bit minimum. So they range from 231 to negative 231. So if you are using those sign number, so you will be able to get your negative number, okay, under the sign number. Okay, you will be able to identify your negative value. This part here, they can cover this range but actually it depends on the hardware that you are available. Okay, so normally minimum, this is what is being mentioned here as minimum. Okay, they range from here to here. That is the maximum that they are talking about. Okay, so the system itself, okay, will automatically, okay, assign a range for you if you never say anything about the range of the integer that you are using. All right, if you never specify. So this type of integer here is being used as an index holder. Sometimes you want to do certain things more than 10 times, more than 20 times, or a specific number of times. All right. So you need to make use of an integer. Let's say you say that n is assigned as a 10. Okay. Then subsequently, okay, n is a, so sorry, this is a number. Okay. You take it as n minus 1. Okay, variable is a colon equal. All right, so this n gradually decrease. Okay, and with this integer here, you find that, okay, they can do those mathematical operation like your add, your subtract, your multiply, your divide. Okay, you can do all this. And last week I mentioned about multiplying, isn't it? So you make your multiply process so easy that if you are multiply 8 bit, 8 bits. If I use a hardware to do it, to be frank, okay, maybe I need to spend 1 day. If I don't want to sort of, okay, having any error, slowly I do it, okay? But VHDL, so away you just key in, okay, 1 line only, they produce you the answer. Okay, so a simple example here mentioned here as how am I going to make use of my integer. So architecture behave of counter is, I begin process. So counter always, okay, controlled by clock. When there is a change in my clock, then you find out, okay, counter will increase by 1. All right. So when there is a change in clock, counter will work 1 time. And here, the variable or counter, okay, name this variable this is the name of the variable that you're using, CNTR. Actually, it's a short form for counter, colon, integer range you specified. Okay, so if you were to specify the range here indirectly, actually you are saving some of the hardware in the hardware that you are using, the D2 board in our lab. Okay, because if you didn't specify this, okay, system will free or allocate this amount of range for you. Use up unnecessarily hardware. So I don't want this. So I specified my range. I say that, okay, I only need from 0 to 63. So 0 to 63, how many bit? So remember, this is 1 bit, 2 bit, okay? 1, 2, 4, 8, 16, 32, 64. So you use only 1, 2, 3, 4, 5, 6, 7 bits. Okay, you use only 7 bit instead of they allocate, okay, this amount of length for you, yeah, which you are wasting the hardware size. Okay, so this integer here, if I put it this way, tells me that start from 0. Default start from 0. But what happens if I didn't put down this? Actually, by default, they also start from 0. But to make it very clear that, okay, we assign our starting value, which start from 0. So this is the, you set the default. So starting value, okay, is 0. So you may need to sort of count up. Later on is a 1 and so on. So this is just a very simple. I declare my variables outside the loop, okay, outside the loop, but inside the process. So begin, so you start to do whatever counting that you want, okay, just to tell you how you are going to use your integer. Okay, so if you are using, okay, to enhance the types of standard, okay, variables, okay, those are predefined, okay, variable. So bit, you got 0 and 1. Okay, default, okay, initialization is set to 0. But some students, okay, they cannot remember whether default is 0 or 1. Okay lah, never mind. I define on my own. I want my starting point start from there, okay? So I put it here. Okay, so in this example here, we look at, okay, a multiplexer. I got an input A, B, and selector is the S. Using bit, purposely want to enhance this one. And my output is also, okay, they will output me the bit value. So indirectly, I'm trying to tell you my input is a combination of 0 and 1, okay, 0 and 1. My S also will be in terms of 0 and 1. Y is also output you a value of 0 and 1. Okay, so from here, you will never define anything here. My Y will start from 0. They will show me a 0 first because this is the default value. Okay, next. My bit vector, okay, is an array of bits. Okay, so look at here. Architecture behave of marks is a constant. I label the name for this constant called low. Name for this constant. So it's a bit vector. So with this one here, I know that, okay, it is more than 1 bit. How many bits? This is a range that you define. 1 down to 0. So 2 bits. 2 bit, where do you want to start from? You suka hati. If you don't put that, by default, they will start from 0, 0. But I want to make it very clear that I want to start from 0, 0. So by default, I set it to start from 0, 0. Take note that double inverted comma. If it's a bit vector, double. Okay, single. Okay, then begin. You start to describe how this architecture is going to perform their function. Okay, so this is the bit. Next, how we are going to use the Boolean types. Like I mentioned earlier, Boolean, you have a true and false, right? The true, we always thought that yes, correct is a right. False means it's something wrong. If you want to use a digital sort of to represent it, you can imagine the true is equivalent to equivalent, not exactly equivalent to 1. False is equivalent to your 0. All right. So look at here, Boolean, true and false only. It is not actually a bit. That's why I use the word here equivalent, not exactly the same. It is a bit literal, not a bit literal, have no relationship to a bit. They are not exactly 0 and 1, but correct, wrong. All right. Now, operations always, use it in if-else statement in process and always produce a Boolean result. Okay, what is all this here? We look at our simple programs over here. So this is a complete programs. That's why I start off with the library for these systems to be able to understand what are the reserved words, what is the meaning of your in, what is the meaning of your Boolean here. You must use those standard library. All right, so you start off with library IEEE. You open up the standard package. You want to use this one, you must open it. How to open it? Use. Put in this word, type in this word, use to open up this. All right. So for all the VHDL program, this is the two. These two must always be written. Then you may have extra library that you want to open. You add it in subsequently. All right. Okay. Then my list entity here, the name is called controller. Okay, entity controller is port. I have a select. Now my select here, the type is labeled as Boolean. Okay, Boolean. Then my X1, X and Y here are the input. So it cannot be Boolean. X and Y are the input. So it's in standard logic. I am going to use 0 or 1 or even the don't care conditions, for my X and Y. Z is the output also, of the form of standard logic. So close my this entity here and my controller. Okay, how am I going to use this Boolean algebra in my architecture? Just look at it. Architecture behavior of controller is I begin. So this is the combinational circuit. So this combinational circuit, having actually one input called X, the other input called Y. Okay, next, another input here is actually the selector input called cell, cell selector input. And I have an output here called set. Now, cell is actually the one decide whether my output is the same as X or my output is the same as the Y input. This is a multiplexer. Okay, example of a multiplexer. So you find that, theoretically, my output for multiplexer is given X. If I want to choose my X as the output, I must make sure that my cell, so I use S to represent cell, must be a 0. Or if I want to choose Y as the output, I must make sure that my cell is a 1. So the outputs here, if I were to write in logic expressions for a multiplexer, actually it is given by this. Okay, by these expressions. And now I'm going to describe it making use of the cell element. Concept may be different now, okay? Suka hati, I can change my list locations, but it indicate, is a true value or false value. And because this is a combinational circuit, every changes here, every changes here will cause this entity to work one time. I repeat, this is a combinational circuit. You are going to find that any changes at this inputs here will cause this device or this entity here to function or to operate one time. Therefore, in this architecture here, under the begin, after the begin, you have your process. Process here is containing your X input, Y input, as well as the cell input. Any one of this one here change, okay, change will cause this whole thing to run one time. No changes, no need to work. Got changes, must work. All right. So the way you write is you begin process. For all combinational circuit, you find that all their input will be listed here. Okay. Then I begin. I check if there's any changes here. I check. Is it my cell change? Okay. If my cell don't change the old cell, then my Z, okay, will be assigned as X. So that is to say that, okay, if my X change, okay, my X change, my value of the Z is going to change, because even though cell never change, but X change, my Z will be having the value of the new X. If X is not the one who's changing, then you check, else my Z, okay, will be the Y. If Y is the one that's changing, maybe now, maybe, okay, I use the word here, maybe, because depending on whether your cell is under what type of condition, then you find that your Z here will be assigned with the value of Y. This and if, tally with this, you got if, you got and if, and you look at the way, okay, they arrange, okay, the coding in line. So this if is for this one, you and this one is for this one. So inside your program may be more than one if. So very difficult to check, okay, if you didn't arrange them properly. In the exam, if you give me everything start from the same line, okay, I straight away, okay, minus your 3 marks first. Okay, nobody write programs in that way. Okay, so after this, okay, process, I must end anything with a begin, okay, you must end it. So process, you begin, so you end the process. This architecture, you have a begin, so you end your architecture. Okay, so architecture, begin, process, begin. Okay, if you have a process, architecture, begin, process, begin. So memorize the sequence. Okay, now I look at this one here again. If cell, then what does it mean by if cell then? So this cell here indicating true. Okay, so if my cell is true, then Z is same as X. Else here indicating that my cell is same as false. But there's no need to write, because you have only two conditions, either true or false. So if it's not true, then must be false. Straight away, okay, if not true, you can jump to these conditions already. So when writing program, normally, okay, we don't write this part. Okay, consider as understood. Okay, I saw, okay, this part here. Would it work if process cell without X and Y in the bracket? Okay. So you are trying to tell me that, Kibun, you are trying to tell me that I don't put X, I don't put Y in my bracket, cell only here, Kibun? Is it your question? Okay, if this is the case, my cell change, I work. But what happens, my X and Y change, I don't call it out and work again. I only wait for cell to change, then only I function. So your answer may be wrong. Kibun, have I answered your question? So whatever changes here, it may cause a different output. So you must put it inside. Okay, you must put it inside. Okay, so write program, try to make it simple, and don't add in unnecessary information. Like you say that, okay, some students argue with me, say that if I put in cell equals to false, clearer, this is not the way of writing program. All right, so we have to stick to the way we write program. So if true, this is the condition. So understood that, else means that cell is false. Z will be assigned as Y. So remember, end it, okay? And remember, okay, the semicolon at every time you want to end certain operations, okay? So true condition, but not necessarily is a one, like I do here, not necessarily one. You can reassign your this condition for your this multiplexers here. Okay. Okay, user define enumeration types like the traffic lights. Before I sort of make use of it, okay, I must declare. So designer got to specify exact values for operation, because you don't want to use whatever the standard so you define on your own so you specify. So will be very useful for your state machine design. State machine actually are your so-called sequential, those are flip-flop, flip-flop design. So flip-flop, you find that may not be just so simple that 0 and 1, these are things here. They may have a step, maybe it's a waiting step, proceed step, whatever you label lah. So how we are going to do it? So you find out we can do it as in this form. Architecture machine of traffic light is, so this entity here is a traffic light. Okay, you declare your type. You say that type. Now the blue one are the reserved word. The black one you define on your own. So type state is, so I have only 3 states: red, yellow, and green. I define this one first. Signal standard is a wire. Now I have 2 signal here: current state, next state. What are the type for this current state and next state? Label here using state. Suka hati saya, whatever name. So what is this state? Refer back to here. State here means that current state could be red, could be yellow, could be green. Same thing, my next state here could be this one, or this one. Because whatever information here is of the types of state. What is contained in the state? These 3 colors. Okay, and this one user define, the designer decide. Okay, so of course this one you decide already, make sure same lah. Okay, make sure they are the same. Otherwise, they will not know that your current state and your next state are of the types of red, yellow, and green. Okay, so the data type of the 2 signal, your current state and next state, is the user defined type called state. Suka hati this is the name you suka hati put down. Okay. So like I mentioned just now, every time, in the VHDL, you must sort of, write this one here. Okay, key in this one first, and it is supported by most VHDL simulator and synthesis tools. The one that we are going to look at is using Quartus 2. Okay, Quartus 2. But if you are using other vendors' VHDL IDE, they can also be supported, because every of these IDE here, they are bounded by this IEEE. IEEE is the one who set the standard. So follow the standards. So you are going to find that our this standard logic 1164 here contains 9 signal strengths, and they can resolve multiple signal assignment. What does it by multiple signal assignment? Later on, I just I go about it later. So it is generally being used instead of bit and bit vector. So you find that we use a standard logic, because it is not so ideal. In the case of hardware, nothing is so perfect that you have only 0 and 1. And sometimes it come out with some condition, cannot define. Don't know whether is it a 0 or 1. So it's a very weak 1 or very weak 0. So therefore, standard logic is more frequent to be used as compared to your bit and bit vector. If it's a standard logic, you want to use it in terms of vector, of course, just add in standard logic vector underscore, standard logic vector or standard logic. All right. Okay, we look at this one here. In general, okay, you also may be seeing that, okay, standard U logic. But we normally don't use it, okay, because they cannot resolve the multiple resolution problems. So we will go for standard logic rather than standard U logic. Okay, so over here, let's look at it. Let's say I have a very simple program. I put it down here. I just start off here with begin under my architecture. Okay, begin. If I were to ask you, I say if I were to return it as a if my select, okay, equals to logic 1, then I say that, okay, my y is the output is assigned as a input. Okay, else, okay, my y is assigned as a b input. Okay, so it's a very simple type of concept. Of course, okay, I can end my if here. Okay, I end my if here. Very simple concept. But you are going to find that my y is either going to take the value of A or the value of B, depends on the select input, isn't it? So my select now is it's not a Boolean. It could be it's a bit or standard logic. So if I were to write this way, you are going to find that if you declare as a U logic, this one, they cannot accept it. But if you describe it as a standard logic, okay, put it in full, okay. If you were to describe it, okay, those signal you use it is a standard logic, then no problems. Why? Because this is a multiple driver. Standard logic can accept, okay, multiple driver allowed. They allow this. But U logic, okay, cannot. They only have one signal driver allowed. So in some books, okay, you see this, okay, maybe it's because of only one signal driver is allowed. But to prevent, okay, confusion later on, okay, I need to have a multiple driver driven component. So it will be easier for us to describe all using standard logic and forget about your standard U logic. But here I need to introduce, just in case you see in some textbook, right? What is this U logic? Is it typo error? No, there are actually these steps. But only one signal driver allowed. This one, multiple. Okay? So inside the tri-state also you can use it. Tri-state actually, okay, related to your multiple driver already. Okay? So conclusion is that standard logic is best choice for behavioral. So I am going to forget about standard U logic, use standard logic only, okay, in all my design that I key in later. Okay, so what are the values, okay, available in the standard logic here? Of course, some common one, okay, that we know, 0, 1, don't care. So don't care, they use dash, okay. And forcing unknown, they use X. High impedance for tri-state, they use Z. Okay, remember I cover the 555 timer. I say, okay, high impedance, okay, you assume it like an open circuit in VHDL, okay, you find that they use Z. So this part here is all under your standard U logic, but it is also available in your standard logic. Same, okay, same. So either all this is in U logic, standard logic also having the same thing, legal values, okay? Because standard logic is a subset of your U logic. Okay, in terms of hardware, okay, because they are talking about a lot of memories. So some of the things you haven't assigned values to it, they use U, uninitialized. You haven't assigned anything to it. Okay, weak unknown. I cannot tell you whether it's logic 1 or logic 0. Same thing, this one here. Okay, but all this not synthesized, okay, cannot be synthesized from for your few. This is few programmable gate array. Okay, it's a type of technology that build up, okay, the hardware for VHDL programs to be downloaded too. So when I talk about FPGA, means a type of technology. Okay, so this type of technology enable the program to be downloaded into it easily. And the hardware that we are going to use in the lab, the DE2 board, is making use of the FPGA technology. So it's a field programmable gate array technology. All right. So if you key in this, yeah, the hardware know what does it mean. They can synthesize and do whatever you want. So this one here, haven't assigned one means they just ignore lah. All right, ignore. And this one here, sorry, okay, because something very big, okay, cannot be determined whether what is the value. Then the hardware will not be doing their task because they cannot decide for you. Should it be a 0 or should it be a 1? Okay, so therefore it's not synthesizable. Only this one, those very clear one, okay, they know. Okay, this don't care here indicating result is either a 0 or 1. Doesn't mean that they really don't care. So the result can be a 0 or 1. So FPGA still can handle it. Result, the value inside that location 0 or 1, either one. Okay, so that's why you put it as don't care. Okay, so these are the conditions in the standard logic. Not so ideal as a bit 0 or 1 only. So they have don't care, they have high impedance. Okay, that's why I always just mention this form. Okay, they have don't care, they have don't care, and the high impedance, okay, in your standard logic, which in reality this is more true. Okay. In VHDL, you are going to find that, okay, they can do, beside logic operations, they can also do things like relational operator. So this is the gate operation. I think no problems. All right. You write this, VHDL know, this is the logic gate N, the logic N, the logic OR, not the English OR. Okay, so they will know what operation they are supposed to carry out. They have this relational operator. This is equal, not equal. So you type it as no spacing in between. Keep in mind. So not equal, when A not equal to B in terms of their values, okay, then you do something. This is greater. If I put A here, B here, B greater than A. This is A greater than B. This is B greater or equal. Greater or equal. This is smaller or equal. I'm using B to refer. Okay, so you can do this type of relational operations in VHDL. You can do n this plus now this plus now is the addition. You add A plus B. Okay, if A is a 5 plus 3, okay, it's a 8. Okay, addition. Not all gate. This is addition, subtraction. Okay, what is this? Okay, what is this? What is this? Anybody want to guess? Okay, what is this? So, concatenate. Okay, this N symbol here is concatenate. What does it mean by concatenate? Let's say if I tell you A concatenate with B. If my A is a 0, it concatenate with B, which is a 1, then result come out is a 0, 1. Not N, but it's combined, both of them together. If I A concatenate B concatenate C, then you find that, okay, result you may obtain in this case here, This is a 0, this is 1, this is 1. For example, result that I'm going to obtain is a 0, 1, 1. So concatenate means that it's like combining. From bit, a single bit, you can concatenate them become vector. Okay, this is a vector. 2 bit is becoming vector already. Okay, useful, this one, useful. Okay, then of course I can have a sign bit. Okay, positive sign, negative sign, the integer, negative number. I can have a multiplying operator. This is multiply. The star here, okay, or asterisk here is a multiply. This is a divide. You got your mode, your remainder. Okay. Double asterisk here means it's power, to a power of. Okay, absolute number related to your max. All these are max. Okay. So if your programs, okay, contain a mixture of all this, okay, then the priority is like that going down. This is of higher priority. They will do this one first, followed by subsequently as in this order. Okay, so priority dropping. Okay, so these are the general things that we are going to sort of, okay, see lah. Okay, next. Important that, okay, if you are using those integer, you either, okay, define your this integer here as a sign or unsigned. Unsigned means that, okay, the MSB bit, okay, MSB bit for unsigned is a value. So for sign, the MSB bit indicating a sign symbol. Okay, if it's a 1, it indicate negative. 0, it indicate is a positive. So therefore, okay, when you are, let's say you need to open up some of the packages at time, for these two here, okay, you can have only one of them. Either you declare your integer here as a signed number or unsigned number, depending on whether signed or unsigned, okay, arithmetic is being used. Okay, so or either one of them. So when you are using those real number, integer, and so on, okay, you may need all this. And these arithmetic operations here is for you to do, say, things like multiply, divide, mode, and so on. So sometimes, okay, when you are writing VHDL program, the time you type, hey, everything logically correct. How come they keep on telling me, okay, there's an error there? It's because you didn't call out the library, so they cannot understand you. What is the symbol of this? Okay, for example, divide. What is symbol of this? They keep on tell you that line got mistake. So sometimes, okay, worth, okay, looking at your this library here. Do I call or open up those necessary library to understand the code or the label, the symbol that I'm using? Okay, so this is under the arithmetic operator. I thought of going to stop here. Yeah, why? Because of something to talk to you. Okay, I will stop here and we continue on Wednesday. Okay, I stop recording first. Okay, this Thursday. Yeah, is it Thursday? A bit blur, okay. Thursday morning we are having lab, right? Last Thursday because I cancel Yeah. Okay. Last day. Thursday. Not Wednesday. Thursday. Okay. We are having lab. Okay. 8 to 10. Right. Now, for me to start off with my lab. Okay. I need your cooperation. Have you downloaded the Quarters 2? Have you downloaded the Quarters 2? Belum belum this is the reason why I want to stop and remind you, okay, to get ready with your